Yeah, let us consider a simple problem to start with. Let's assume that we have some frictionless surface. So once we say we have a frictionless surface, that means we have no dissipative effect. So we have a frictionless surface. And let's assume that we have two masses, m1 and another mass, m2. So now these two masses are connected by three springs of constants k1, k2 and k3. So what do we have if we summarize? We have two masses, we have three springs, we have a frictionless surface, we still need to define the direction in which these masses are moving. So let's say I call this x1 and this is x2. So these are our generalized coordinates are x1 and x2, right? So our goal is to first, what's our goal? Determine equation of motion for both the mass, for both masses, and B, determine our natural frequency. So let's call it as omega 1 and omega 2. So omega 1 corresponds to the natural frequency for mass m1 and omega 2 corresponds to the natural frequency for mass m2. So first question is, we want to write our free body diagram, right? So let's say if we are looking at our Newtonian approach, let's say, so we want to write our free body diagram. We will also look at how to solve the same problem with the Lagrangian approach or Euler-Lagrange equations. But for now, let's start with our Newtonian approach, right? Newtonian approach. So if we are looking at our Lagrangian approach, we don't really need to know the free body diagram. But if you are looking at a Newtonian approach, we are looking at the forces. So we need the free body diagram. So one thing that when we write our free body diagram is we want to isolate all our masses, so m1 and m2. All the connections are simplified in terms of what is the force acting, right? So now let us say if I would think that my mass m1 is moving to the right hand side, that would mean that this spring k1 is stretched a bit, right? That means it's going to pull the mass m1 back so that the spring k1 comes back to its original state, right? So m1 has moved to the right. So if we think about it, so let's say we had this spring k1 and we had the mass m1. So now once it starts to deform, we said the mass m1 has moved a bit to the right, right? So this is an old position and this is our new position. So I can say that if this was the old position and this is the new position, this is probably x1, which means this spring is elongated by x1. Right? So because it's elongated, or it's the intention, it is going to come, it wants to come back to its original state. So I can think that the spring force is acting in this particular direction for the mass m1. So let's try to write these spring forces. So I have spring force from Fs1, and so I'll say spring force because of the spring 1, right? So now similarly, let us assume that our mass m2 was probably in a particular position, right? And I have a spring k3 and it's probably moved to the right. So again I can say the distance here, let's say, is x2, and that means my spring here has been compressed. So the spring here is extended, spring was extended, the spring, while here we compress the spring. Right? That means the spring here is going to be pushing the mass m3 in a particular direction. Let's say I call it spring force S3, right? So if I'm going to write that here, say spring force S3. Sorry, I got that wrong here. Okay, so now that means that my spring on one side is pulling. The M1 is basically pulling it to the left hand side. So for example, this is pulling it to the left hand side and is pushing from the right hand side. So now one thing that we assumed here is that the mass M1 is moving rightwards. So this is our assumption we have made. Let me take a different color. We assume that mass M1 is moving rightwards. Mass M2 also has moved rightwards, right? Move direction, let's say. And again also the moving direction. So now the mass M1 has moved by x1 and mass M2 has moved by x2. So depending on whether x1 is greater than x2 or x1 is less than x2, right? If x1 is greater than x2, right? So mass M1 has moved more than the mass M2 has moved. That means the spring K2 goes into compression, right? So that means K2 is compressed. So now if x1 is less than x2, mass M1 has moved, let's say 1 millimeter, but mass x2 has moved 2 millimeters. That means the spring K2 is in tension. A priori, maybe we don't know if x1 is greater than x2 or x2 is greater than x1, but it does not matter. As we will try to see, it does not really matter what we assume. So by default, so let's assume that x1 is greater than x2, just to start with, right? Without loss of generality, we can assume that x1 is greater than x2. And we are not going to lose anything by doing that, okay? So let's assume that x1 is greater than x2. That means the spring is compressed. So let's assume x1 is greater than x2. That means spring K2 is compressed. So now let me go back and rewrite our free body diagram that we had. So we had M1, we had M2. So we had a force because of the spring 3, and we also had a force because of the spring 1. Now we assume that the spring is compressed. That means it wants to go back to its original state, right? So it is going to push the mass M1 to the left side, because that's the way. If let's say if I fix somehow artificially fix M2, right, then only way for the spring 2 to uncompress is by pushing the mass M1 to the left, right? So that's the easy way to think. Let's say if I fix everything else, how is the spring going to move this particular mass? It's going to push it to the left. So I can say spring S2, right? Similarly, if I artificially fix this mass M1, only way for the spring to come back to its original state is by pushing the mass M2 to the right. So I can say again spring S2, force because of the spring S2, right? And since we assumed that, so I can say here the spring force is nothing but K into x1. Similarly, I can say spring force here is K3, so it's K1 into x1, K3 into x3. And again, this spring force is nothing but K2 into x1 minus x2. So x1 minus x2 is the net compression, and spring force K2 is the spring constant. So that is essentially gives us our all the forces acting on this particular system. So now I'm going to go ahead and try to write my equation of motion. So for equation of motion for mass 1, so equation of motion for mass 1, right? So let's say, so that's nothing but mass into acceleration is equal to summation of all forces, right? So if I do this, I only have one direction. So that means mass into x1 double dot is equal to, let's assume that this is our positive direction, right? Right is our positive. So that means I can say minus, k1 x1 minus k2 into x1 minus x2, right? Or in other words, I can write the equation of motion for mass m1 as m1, sorry, let me write that, into x1 double dot plus x1 into k1 plus k2 minus k2 into x2 equal to 0. Okay. Similarly, I can write the equation of motion for mass m2. I can say summation of f is equal to mass into acceleration. So here again I can assume that m2 into x2 double dot is equal to, so fs2 is acting to the right hand side, right? So it's acting in the positive direction. So I can say k2 into x1 minus x2, and the spring x3 is acting in the left, along the left direction. So minus k3 into x3, right? Or I can write, sorry, x2. There is no x3 here, my mistake. So this would be x2, right? So this would be x2. k3 into x2, right? Or in other words, I can write m2 x2 double dot minus k2 into x1 plus x2 into k2 plus k3 is equal to 0. Okay, so let's take a hypothetical situation, or let's say summarizing our equation of motion. So we have m1 x1 double dot plus k1 plus k2 into x1 minus k2 into x2 equal to 0. m2 into x2 double dot minus k2 into x1 plus k2 plus k3 into x2 equal to 0. Okay, so those are our two equations of motion. So now one thing that probably comes back as a question, what if we assumed x1 is less than x2, right? So let's say we had assumed here that x1 is greater than x2. That's an assumption we made. What if we assume that kx1 is greater than x2, right? So let's try to write that here. So let's start with assumption. Let's assume, what if we assume x1 is less than x2. That implies spring k2 is stretched, right? That implies that our force in the spring S2 is k2. So it's a tensile force. So it's going to be minus x1, right? So tensile force. So here x1 minus x2, we said it's a x1 is greater than x2. So we have a compressive force in a particular direction, right? Again, one could also say that k2 into x2 minus x1 is the right thing because it's going to be the compressive force, or right? Or we, right? So essentially we can say x2 minus x1, and then essentially if we are going back to write our equation of motion, so let's say we try to write our free body diagram again. So we take m1, m2. So we already know that fs1 is acting in this direction and fs3 is also acting in this direction, right? So we know these values also. So we know this is nothing but k1 into x1. We also know this is nothing but k2 into, sorry, k3 into x2, right? So now that we have our spring in compression, or sorry, in tension, it is stretched. So it's tension, so spring wants to come back to its original state. So hypothetically, if I assume that the mass m2 is fixed, right? So only way for it to come back to its original state is by pulling m1 to the right hand side. So only way it can unstretch is if it's going to pull it to the right hand side. Same thing with our mass m2. Only way for it to come back to the original state is if it's going to pull m2 to the left side, right? So only way for it to do is fs2. So now if we go back and write our equation of motion, so again let's write our equation of motion. So again this we can write these two spring forces as k2 into x2 minus x1. So equation of motion. So let's say we say mass m1. So then we can say m into a is summation of forces. So m into x1 double dot is nothing but, so x1 is force due to spring 1 is acting in a negative direction into x1, and force due to spring 2 is acting in the positive direction. So that's nothing but k2 into x2 minus x1. Or if I was to simplify, I get m1 x1 double dot plus x1 into k1 plus k2 minus k2 into x2 equal to 0. Similarly for mass m2, we have again ma, so m2 let's make k equal to summation of all forces. So if we go back here, so our S3 is acting in the left direction. Both the forces are acting along the left direction. So we have said that this is our positive direction. So I can then say m2 into x2 double dot is nothing but minus k3 into x2 minus k2 into x2 minus x1. Or if I were to simplify, I have m2 x2 double dot plus minus k2 into x1 plus k2 plus k3 into x2 equal to 0. Or in other words, our equation, these are our equations of motion. Now let's just try to copy paste what we had before. This is now and this is before, right? So if you look at it before, let's try to copy paste that. Copy. Oops. Paste. So this is our before, right? So if you look at it, so term by term, we can, let's say m1 x1 double dot k1 plus k2 into x1 minus k2 x2, let's say. Similarly m2 x2 double dot k2 into x1 k2 plus k3 into x2. So irrespective of whether you assumed x1 is greater than x2 or x2 is greater than x1, you get the same equation of motion and you should be able to get the same solution. Here we didn't assume that anything to do with compressive or tensile forces. We assumed, we gave the direction later based on what direction the force is acting. So we got the magnitude of the force depending on x1 minus x2 or x2 minus x1 into k, and then we essentially put that into our force equilibrium in order to get our equation of motion. I hope this is helpful to understand how to write a free body diagram for a simple problem, and how to think about the direction in which the force is acting, and to determine the equation of motion.